Hi, and this is question 4, and I think it's on bearings. I'm going to start with a quick recap on bearings. Bearings, we always start with some kind of north, right? And let's say we have 2 points, point A going to point B. And let's say we say what is the bearing of B from A? If it's from A, then what we do is we actually put the north from A, so we put the north at A first. Like this. Something like this. And then the bearing of B from A is simply from the north, we go down this angle. Right? If I say what is the bearing of A from B, then actually I need to take my north. So I'm gonna create another north. Or should I say I need to put a north here. Bearing of A, I do not actually go the direction. I always go clockwise. So bearing of A from B is from this all the way here. This is bearing of A from B. Always go clockwise. Yep. Once again, if you say from B, that's why you put your north at B, and then you go clockwise until you reach the line joining it to A. There you go. And one more thing to note about bearings is that they always take up 3 digits or sometimes 4. So for example, examples of bearings could be 0, 1, 8 degrees. So this extra 0 in front, we don't usually write it, but for bearings we have to. Or if it's, let's say, 3 digits, maybe 125 degrees, that is fine. Or it can also be 120, let's say, then 25.3 degrees. This is also fine. All these are good. You cannot write 18 degrees. No. Never. Yep. So this is basically a quick recap of bearings. Okay, now let's jump right into it. A, B, and C, 3 points on level ground. The bearing of B from A is 70 degrees. So immediately you can write it down really. Of B from A, since it's already, A already has the north here. So of B from A is simply this. This is 070 degrees. Or 70 degrees, yeah. And BAC is 40 degrees, okay, over here. And it's given that C is 5 km due south of B. So that actually tells me this is north, this is south. North and south. So these two lines are actually parallel. Yeah. So now we need to calculate the bearing of C from A. So basically for this one, of C from A, so we start at A, the north is there, and we go clockwise until we reach C. We're looking for this. Okay, that's easy, and that's just 70 degrees plus 40 degrees. 110. So this is actually, simply put, 110 degrees. Okay, now the distance of C from A, so we're looking for what? Of C from A, but it's not a bearing, it's a distance, so we're looking for this distance. From A, if you walk to C, what is this distance? And the way we can do it, I think, is we need to look at triangles. So right now, just now I said these two lines are parallel because this is due south, right? This is due south. This is perfect, right? North to south. It says, right, because it says C is due south from B. That means the way you get from B to C is you just drop down to a south. You drop down to south. So they will be parallel. And if I were to quickly highlight this over here, then this Z, right? Because if these two are parallel, then 70 degrees by alternate angles, this must also be 70 degrees, right? Because it says that, because they're parallel. So ABC, I can say angle ABC. Now this is how will I? Is actually equal to 70 degrees as well. by alternate angles. And then I can find this angle. So ACB is simply 180 minus 40 minus 70, and it also gives me 70 degrees. And this is by angles in a triangle. Yeah, that's cool. So this is also 70 degrees. So it tells me that this is an isosceles triangle. That means I can actually drop a perpendicular here, and it will divide this triangle into two. Yeah, and I cannot, now you might be tempted to say, let me just drop it and assume that it's equal, but it's not equal. You must first show it's an isosceles triangle. Then you know you can drop a perpendicular, and then you know that this, therefore, since it's isosceles triangle, is 20 degrees. And since BC is 5, then this is 2.5. And this is 2.5, which is just 5, which is just 5 divided by 2, equals to 2.5. Yeah, and so right now, we are closer to finding AC, because right now we can look at this triangle below here. And let me just draw it separately. Okay, like this. So this would be 70. This is 2.5. And this is 20 degrees as well. Right, this is 20 degrees. Okay, now it's starting to look a bit clearer, because I'm trying to find this. I can use sine rule. I can say sine 20 degrees over 2.5 equals to, this was 90 degrees, equals to sine of 90 degrees over AC. I can do that. And then you will see, when you try to simplify it, is that AC multiplied by, if you cross multiply, equals to 2.5 over sine 90, and AC equals to 7.31. Alright. Right now, part III, the shortest distance from B to AC. So from B to AC. So every time they say shortest distance, you can really think is basically not a curve. It has to be a straight line. And if you think about it, which line is longer, right? Is this line longer or this line longer? Or should I say which line is shortest? Actually, the shortest line is, if you can see, is this one, where it's perpendicular, right? That would be your shortest line. So I'm just going to erase and create some space. Okay. So the good news is we've already calculated that this is a 7.31, right? And we actually don't really, we don't really need this line. Yeah. And what we need to do is you just drop a perpendicular down. And let's see if we can find this distance. And it's always useful to call this part x, right, where it meets this part x. So we're trying to find bx. Basically, we're trying to find bx. And let me do my working over here, maybe. So how to find bx? Let me look at, so basically let me just look at this triangle, and this is b, and this is x, and this is 40 degrees, and this is 7.31. But I'm going to use the calculator value to more SF, okay? So yeah, it is rounding off to 7.31. But I'm going to use this value. And I know this is 90 degrees, right? That is the nature of the shortest distance. Now I think I can do it, because I do know that this is an isosceles triangle. So if this is 7.31, this must be 7.31 as well. This is also 7.309511, right? Now we can do it. We can say sine of 40 degrees equals to opposite over hypotenuse. And then we can solve. Bx is therefore 4.70. There we go. Alright. Now let's do part B. Another point D is due east of C. So that's interesting. I'm going to say that D east of C. So from C, since north is like perfectly vertical, so it's always north, south, east, west. So from C, it's a east. Okay, this is an imperfect drawing, but just bear with me. It's a point D. And since it's perfect east, right, this must be 90 degrees. It must be. And this is 7 km, so this is 7 km. Calculate the bearing of D from B. Okay. So it's trying to ask you D from B. So let's put the north here. And since this was a perfectly straight line, north and south, so really it's fine to say that it's like this. Like that. D from B, is what we're looking for. Right? Yep. Okay. For this triangle, I think what we can do is that we can try to find what this angle is. Right? So we can say angle, I have to write it over here, angle DBC. And actually I don't really know what it is, but if you look at it like this, it is 90 degrees. I can say tangent of this angle is opposite over adjacent. So I can say tangent of this angle is opposite over adjacent. And so this angle itself, this angle, is tangent inverse of 7 over 5. Right. Okay, that really helps, because now I can say that angle, or should I say that the bearing, this angle, so let's call this is that n, okay, let's just call this y. Okay, this is point y. So I can say that angle YBD, right, which is just this angle with YBD, is basically 180 degrees minus away this angle, and this angle DBC was this tangent inverse 7 over 5. Yep. And when all is said and done, we calculate it and get 1 to 5.54. It's a bearing, so it's always like this, right? 1 to 6. I think that's sufficient. There you go.